Right, let's move on to the second section. I mean, chapter 2 in part 1. Here we will focus on squares and square roots. Okay, but before we move on to this chapter or deep dive on it, let's just try to uh, correct some understanding that I covered in part 1, chapter 1. So, while covering this, okay, let me just repeat this part. So, in the number categories, there is a category called real numbers, and real numbers are divided into two categories. One is rational numbers and the second one is irrational numbers. Rational numbers will cover all the kind of fractions, ratios, positive, negative, numbers, integers, everything. But what he won't cover is a few things which are kind of repetitive numbers, repetitive fractions, ratios, or kind of indeterminate kind of numbers. Those are called irrational numbers. Now, so come some examples of that are given here. Now, in mathematics, the irrational numbers are all the real numbers that are not rational numbers. So, whatever possible numbers are there, those are rational, which we mostly deal in day-to-day life. But there are something which is not rational and categorized as irrational numbers. Examples, something like pi. Now, what is pi? It's a ratio and primarily used in calculating. One of its use is calculating circles circumference by multiplying the circle's diameter to pi. So there is one use. There are many other uses like spheres or cylinders also. And the second example of now why it is called irrational number, the pi, because again we covered, right, what is 22 by 7. It is a fraction with 6-digit repeating blocks, so it's never ending, that's why. And then there is another category, there is another example which is kind of square root of 2, that is also never ending. So these are few examples of irrational numbers. There is also some indeterminate numbers like per se 1 by 0, that is indeterminate, that is also a irrational number category. So what is not rational, that is irrational. So if you consider all numbers to the universe of real numbers, then it could be one rational number, one is irrational number. Rational numbers will contain integers, natural numbers, whole numbers, positive, negative, fractions, ratios, and everything, which are kind of determinate kind of stuff. So that's the kind of little clarity I wanted to do for the chapter 1. Now let's move to part 1, chapter 2. So coming to part 1, chapter 2, sorry, squares and square roots. Again, this is not the chapter 2 in the textbook, but this is the part 1, that how I have categorized 5 chapters as part 1 for easier understanding. So it is kind of the next chapter in that sense. So now what is it? Let's just try squares and square root chapter. Then okay, and just taking a little more time, but we are on it. Alright, let's move to chapter 2 quickly. Squares and square roots. So we know many number relations, but there is a category called squares and square roots also. Now what is it? Let's see in detail. What is a square number? If a natural number can be expressed as a square, per se r square, where r is also a natural number, then s is called as a square number or perfect square. So that's the simple. So if you can represent a natural number called s in the form of r square, where r is also a natural number, then s will be called as a perfect square. So that's the understanding we will move on with. Next, examples are kind of 1, 4, 9, 16. So per se 4 can be represented as 2 square, 9 can be represented as 3 square, 16 can be represented as 4 square, hence on and henceforth. Property. Property of a square number. What's the property of a square number? First property is it ends with either 0, 1, 4, 5, 6 or 9. Now, how to cross check whatever the property we are saying is correct or not? So, if you're saying go and check the squares of squares from 1 to 20, you will know. Now, patterns of square numbers. What are the patterns? Two consecutive triangular numbers can give a perfect square. So this is the pattern. This is also part of the property, but the book explains it. Okay, remember it like this, it would be easier. So it's saying two consecutive triangular numbers can give a perfect square. Now what are the two consecutive triangular numbers? Is that okay? So in the example here given is 1 and 3. So 1 and 3 are two consecutive triangular numbers, which if you sum them, it becomes 4. So that's a perfect square. What is a triangular number? That also picture is given in the book. I see. Let me see if it is there here. It doesn't look like the picture is here, but it's there in the book. Triangular numbers are numbers which is kind of represented in a triangular form, like per se before 3, 0, 1, 2, 0, 1, 2. If you add all of them, this becomes 3, and then similarly, 6 is also a triangular number, 10 is also a triangular number. If you look into the book, you will know. So it's just a pattern saying that. Also, if you see triangular numbers are 1, 3, 6, and 10. And if you add any of the consecutive triangular numbers, that will give you a perfect square. I know I could have explained it better. I will try to in the next chapter with some pictures. But meantime, you just remember this triangular numbers, consecutive triangular numbers addition gives you a perfect square. And then coming to the next pattern, there are 2n non-perfect square numbers between the square of numbers n and n plus 1. So this is also another pattern or property. What you can say is that there are two and non-perfect square numbers between the square of numbers n and n plus 2. So per se here in the example it is considering n as 2, n plus 1 is 3, which is 4 and 9. So it's saying that Between 4 and 9, there are 2n non-perfect square numbers. And what is that? Between 4 and 9, if you square these, and between 4 and 9, and between that 4 and 9, you have 5, 6, 7, and 8. So which is kind of 2n, 4 numbers. If n is 2, then 2n is 4. So there are 4 non-perfect square numbers between two perfect squares. So that's the another one. Now coming to the another pattern or property, what is that? It's saying a perfect square can be expressed as sum of consecutive odd natural numbers starting with 1. So a perfect square can be expressed as sum of consecutive odd natural numbers starting with 1. This is also a very interesting property. So the example given here is 1, 4, 9, and 16, right? So, so, uh, so it is saying is that okay, these are the perfect squares. Then you can represent these perfect square individually 4 and 9 and all a sum of consecutive odd natural numbers. So that is also there. You can see the figure and image in the book. I could have included that, but it's directly from the textbook. You can look at it. Okay. Next. Uh, Next pattern. Square of any odd number can be represented as sum of two consecutive positive integers. So square of any odd number, okay, can be represented as sum of two consecutive positive integers. Right. So this is also another property. It is talking that you take a square of any odd number, per se. Um, any odd number means per se, you can say odd means 3. Let's consider 3, and its square is 9, and can be represented 9 can be represented as sum of two consecutive positive integers. So 9 can be represented as two consecutive positive integers 4 and 5. So 4 plus 5 equal to 9. Okay, so these are properties. I really don't know how we can use it in problem solving, but these properties, knowing these properties, are interesting in the sense that you will fall with numbers. You will fall in love with numbers, and that's what the overall intention is. That okay, you know these properties. These are interesting properties. So knowing these, maybe if you can apply it once in a while, the calculations will be faster, or the understanding will be faster. Just like that. There is another property. This is also kind of called as a expression or equation. Is that a plus 1 a multiplied by a minus 1 equal to a square minus 1. So, and then we have some examples of some interesting patterns. These are just patterns, guys. That means how 1 square is represented, how 11 square is represented, how 1 square is represented. If you see, in 11 square there is 1 to 1, and in 1 square you have seeing that middle number is 3, and either side there is 2 1 2 1. So those are kind of interesting patterns, just for your understanding. Let's move on. For any number representation a5 square equal to what is that? So any number representation a multiplied by 5, a multiplied by 5 whole square equal to what? It's saying a multiplied by a plus 1 plus 25 where 25 square equal to 2 multiplied by 3, 25. Okay, for any given, so this is also kind of an interesting pattern that it's represents it's with a formula. So this is the formula, like per se, if a number is there with a and 5, and then you can represent it like that. Now let's try it. Um, per se, we'll try it with. Yeah, this is also a pattern, and if you remember this, represent this, then you will understand. So first focus should be this formula, this representation, which is saying that A5 is a representation where it's saying that unit digits is 5, and the previous one is considering A, so that can be represented as this one. So if the previous one is per se 2, then this would be 2 plus 3. 2 plus 3, right, 2 plus 3 is kind of 6. Now 6, this plus sign is wrong, it should be 625. So 25 square is 625. Similarly, it's giving an example that, yeah, it's given to 25 square, it has represented. So it's saying that a multiplied by a plus 100 plus 25, and this is how it is represented, 100 plus 25. Similarly, it's representing 35 also. The next pattern is Pythagorean triplets. Now, what is a Pythagorean triplet? This is very interesting. So, knowing what is a Pythagorean triplet, first you know what is the Pythagorean principle or rule, right? So, I hope in earlier standards you might have known about it, but I will cover a little bit. For any natural number n greater than 1, this holds true that 2n whole square plus n square minus 1 whole square equal to n square plus 1 whole square. Hence, it is saying that 2n n square minus 1 and n square plus 1 form a Pythagorean triplet. So this Pythagorean means it's kind of a rectangle relation per se. If you know about rectangle, sorry, not rectangle, it's kind of a triangle with a 90-degree. There only this Pythagorean principle comes, where ABC is the triangle and C is kind of a diagonal, then A square plus B square equal to C square, and that's what it is, like 3 square plus 4 square equal to 5 square, and similarly 6 square plus 8 square equal to 10 square. Now they are saying that how you can find more of these Pythagorean triplets. If you know this formula, you can reverse engineer it, like putting replace n with some number 1, 2, 3, 4, whatever it is, and you can get many of these Pythagorean triplets. That's overall thing. This is just passion about numbers and different ways to figure out various numbers. Knowing this is going to be helpful, but it's really not that you need to by heart these things, but remembering these patterns is kind of helpful in solving various problems. Now let's move on to next, square roots. So squares we are done with, all the properties, patterns and all, that's all constitute squares. Now coming to square roots, what is a square root? Square root is an inverse operation of square, just like addition and subtraction. So per se, if addition is an operation, subtraction is the inverse operation of addition. Multiplication is an operation, division is an inverse operation of multiplication. Similarly, it is saying that if square is an operation, square root is an inverse operation of square, and that's the best way it can be represented. Now coming to next, square root of 9 is 3. Square root of 16 is 4. So it's just the inverse operation. 4 square equal to 16, 3 square equal to 9. And then you do square root, you will get the original number. Ways to find square roots. Next topic. Facts. Sum of first n odd numbers is n square. So this is again guys a property and a formula you can remember. Remembering this will help you in the calculations, that's all. Sum of first n odd numbers is n square. If you put n with some number, then you can figure out how it is calculated to. Hence, square root of n square is the number of odd natural numbers. So this is just a fact. So square root of n square is number of odd natural numbers. It adds up to that is n. It's pretty simple. So more you can see in the examples in the book where it explains what it is talking. Sum of first n odd numbers is n square, how it happened. Next one is square root can be found out by prime factorization. Yeah, there is a way to find the square root using prime factorization. We will discuss that going forward. I have a way to do that. I tried to do that in a slide format, but yeah, I hope I can able to cover that here. But usually those things better done in paper and pencil is easier, but we have tried. So prime factorization is a way to figure out square root, that is representing a number by multiplication of initial prime number starting from 2 and then pairing the series. So this is just saying what is prime factorization. Okay, we will know when we do one example. We will be having proper clarity on this. So per se this one. Now per se I want to figure out what is the square root of 6400. Now I need to find it out by prime factorization. The prime factorization says is that how to do the prime factorization of 6400 is that we try to represent the number by multiplication of initial prime numbers. Per se, if it could be represented by multiplication of initial prime numbers like 2, 3, 4, 5, 7, not 4, 2, 3, 5, 7, so on and so forth. So I tried to do it and I could see that okay, is on when I can do with 2, I went on do with 2, 2 multiplied by 2 multiplied by 2, and after that it reached like 5. I can represent it with 5 prime number and again a prime number. Now you say to find the square root you need to pair them and then you will get the result. Now how it is? Per se, then there are two 2's are going to considered as kind of 1 2. Again here 1 2, here 1 2, here 1 2, and here 1 5. So that means there are 4 2's and 1 5. 4 2's multiplied give you 16 and 5 means 80. So 80 square is 6400. That's the prime factorization way. Here it is saying when you do in paper and pencil, you do like that. First try with the initial prime numbers 2, it will become 3200, again 2, 1600, again divide by 2, it becomes 800, again divide by 2, 400, again divide by 2, 200, again divide by 2, 100, and then again divide by 2, 50, and again you divide 50 by 2, it becomes 25, which can be represented as 5 by 5 because you cannot divide 25 by 2 or 3. So you need to divide it by 5 and that remainder is 5. Now this says that okay, this is a perfect square because you got pairs of natural numbers and you can pair them and figure out the exact value. Now let's move on to the next trick. So there are tricks and properties continued for square root the way we continued for squares. It's not obvious to find the square root of large numbers, hence how to find it out. Let's find that. So it's just showing below some square root for whole numbers and decimals, that you will understand how to find the square root. Facts. We can say that if a perfect square is n digits, then square root will have n by 2 digits. Okay, so perfect square has n digits, square root will have n by 2 digits. So per se, if the perfect square has 4 digits, square root will have 2 digits. For n is even, or n plus 1 by 2 digits for n is odd. It's just saying you a property how we can represent a square and a perfect square and perfect square and a square root. So you will get to know this once you do more and more examples on these, right? So example here continued. For 3 digit perfect square, square root is 2. So if it is a 4 digit perfect square, then square root will be 2. For 3 digit also it will be 2, because it's for odd numbers it is n plus 1 by 2. Then for 4 digit it is 2. It's just giving an example how what is the meaning of this fact with a simple example. Now here, calculating the square root by using the prime factorization. This kind of example. So here it is considering 529. Now 529 is there. So what you will do? 529, and then you will do prime factorization. You will do 2, 2, and you will put 4 here, and then that reminds you from this 5 minus 4 you will do a carry forward of 1, and then this 29 pair you will do 129. So whenever representing a square root calculation, you from right side you pair it out, and then whatever remaining that remains as a single digit. So then it would be easier for you to calculate. But say here 529 you paid 29, here 5. So you are now calculating by prime factorization. 2 multiplied by 2 equal to 4 you put. So that covers the 5 one, because you cannot do 6 because it's 5. And then you subtract it, you become 1, and the next pair you bring down 129. And then here what you are doing is here you kept 2, right? Now this is kind of your figuring out square root. So when in the below you are going to put 2, the kind of 2 square. If you do 4, you will keep it here, and then you need to match up to 129. So 3 here, and you will put 3 there, and then that is giving 129 is 0. So that is saying that 529 is a perfect square. And what is the square root? 23. That's how you take it. Okay, this is one example. Next. So this is a decimal, very interesting how things are done in decimal. Again, you are going to do from, in case of decimal, you will start the pairing from the left side. If there is more digits in the right, it will go 2 pair here, then 2 pair here. But in this case, it will go from the left side, the pairing will go this side. So it's saying 70 is a pair, dot 64 is a pair. Now 17 means what square you can do? The square root of 17, the best you can do is 4, 4, which is giving you 16, right? And here I said wrong, it's not 2 square, it's a double of that. So here 4 is there, so you will keep double of that, 8 here. And then this is 1 here, and you bring the 64 here. You will put a dot because dot is here. So this is 82. And you see 164, you put a 2 here, so it is 4.2, and this turns out to be a 0. So the whole answer is that 17.64 square root is 4.2. This is how, this is a technique to figure out square root using calculations of prime factorization. So this is kind of a division formula. Earlier we saw something called the prime factorization way. Here is also, but prime factorization you cannot able to do with respect to decimals and all. So this is so that's the reason for in case of decimals or fragments, they said okay, if you do this division kind of formula, it would be easier for you. So that's how it is shown. So for perfect squares, this kind of formula is going to work. This prime factorization will work. But which is not a perfect square, this formula won't work. That technique of thing not going to work. This division way is going to work, and division way will work for non-perfect squares. I mean regular numbers which are not perfect squares, and also for decimals also which are not perfect squares. So to figure out whether it's not always easier to figure out whether it is a perfect square or not unless you go through the process. But this technique of doing it will always help you. So whether it is a perfect square or not, you will get some result. So, and that's the overall thing. So how to find a square root of a number which is not a perfect square. Per se, this is a perfect square, 529, but 17.64 is not a perfect square. Now, how to find it out? So, this is another technique it is showing to find it out. Examples: how many natural numbers lie between 15 square and 16 square? If you remember, in the um, property of squares, we decided a formula to how to do. So we use that formula here. Between squares of any two consecutive number, there lies 2m natural numbers, where m is the smaller of the two consecutive numbers. So this is what saying. So that means here 15, 16, where m is the smaller means m is equal to 15. So 2m, that means 2 into 15, 30. So there are 30 numbers lie in between. So this is what saying, one of the property used, 30 numbers lying in between these. Find the smallest square number that is divisible by each of the numbers 4, 9 and 10. How to find it? Smallest square number that is divisible by each of the number. So then I think for this kind of question, how will you figure it out? So you need to know what are the common factors, then only you can able to figure out what is the smallest square number. Now let's see how we are solving it. The number should have all prime factors in each of these individual numbers. So per se, if you know what are the common factors in 2, what are the common factors in 9, what are the common factors in 10. Now if you figure out a number which is multiplication of so and so prime numbers which holds all the prime numbers required by 4, 9 and 10, then that's the smallest number. It's saying that see, 4 equal to 2 multiplied by 2, 9 equal to 3 multiplied by 3, 10 equal to 2 by 2 multiplied by 5. So you take both 2's, then it will work for 4 and also help for 10 also. So 2 2's, 2 3's and 1 5 will take care. That's what the conclusion. See, this is how it is calculated. 180. Again, these are the few applications we got to know how to use it. So I tried to cover few examples and also few interesting problems from outside. But unless you practice each and every entry, this is mathematics guys, unless you practice each and every exercise, you can't be expert. So practice all the exercises in the textbook, that can only make you perfect. Okay, and that's it for chapter 2. Next chapter we'll cover cubes and cube roots. Thank you.